In this video, we're going to be looking at the concept of collisions and explosions by applying centers of mass to them. What are we going to do? We're going to review Newton's first law of motion and apply that to systems where we have moving objects, but even though the objects are moving, the system itself as a whole will actually be remaining stationary. We're also going to look at situations in where centers of mass will not be able to work in our systems and why that's going to be. And for those systems that we can use centers of mass, we're going to look at how we can use the center of mass then to calculate the point where objects will collide, or if something explodes, how we can use centers of mass to find a piece of that object after the explosion. Why are we doing this? Systems with many moving parts can be very complicated if you view every object separately. There's a lot of moving parts. But centers of mass simplify the situation down to a single point that's easily manipulated. This is a key starting process in solving complicated problems. It's not the only problem, but now you have a complicated problem with a lot of moving pieces. It's best to simplify it down initially, see how the group is moving, and then once you take a look and see how the group is handling things as a whole, you then go back into the individual pieces. But once you have the big picture, it's much easier to understand what's happening with the pieces inside it. So we're looking at step one of a very complicated problem-solving process today. Now, Newton's first law of motion is, again, the law of inertia, and we're not going with the oversimplified ways of saying things. The law of inertia really is that an object or a system's motion does not change. That means the speed is constant, the direction that speed is moving in is constant. If it's not moving, then that's the speed with a direction. It's nothing, and that's fine. So whatever the object is doing, that remains constant unless there is a net unbalanced external force acting on that object. So again, we can have multiple forces from the outside acting on this system or object. If they all balance out, then it's just like there's no net force on me. But if there's an unbalance in those forces, then there will be a change in the object's motion, either speed, direction, or both. It's very important for you to realize that when we are talking about the motion of a system versus the motion of the pieces that are inside the system, they could actually be very different. It's a lot like your grades. If you have an 85 average for a course, it doesn't mean all of your grades were an 85. In fact, it's entirely possible that your grade average for a course never showed up on any of your tests, quizzes, or homeworks. In fact, that's most likely the case because when you look at your average, it's never really an 85. It's more like a 85.2 or a 84.97. And I don't think there are too many teachers out there that give grades like an 85.2 on a test or a homework assignment. So your average doesn't necessarily have to be the same as any of your test grades or homework grades, and the motion of a system, which would be the average motion of all the objects, doesn't have to equal the motion of any of the objects. So here we have two asteroids. They are separated out. Their masses are not equal, and because of the force of gravity between them, they will eventually collide and have a collision. There will be an explosion. It will look very bright, most likely, possibly. At least it will look good for theater. But do both objects travel the same distance? Where do they meet? And that's going to be where we use centers of mass. If I look at these two objects and they are initially stationary, then the center of mass of the motion of the center of mass is stationary. The system isn't moving. As these two guys get pulled towards one another, they will get pulled to the center of mass. But that center of mass still has not moved because there is no external force. Now, if you're wondering why is it then that these objects move, that's because the force of gravity that pulls on them both is in fact internal for the system, But if I am looking at just this asteroid, the force of gravity that's pulling on just that asteroid from its point of view is external. The other asteroid's pulling on me. And the larger asteroid, that force of gravity is, from its point of view, external because it's coming from the smaller asteroid. If we're on the outside looking at the two asteroids together as one system, then we can say, you know what, as a system, those forces are internal. And so there is no external force on the system, so the center of mass will not move because initially it's at rest. Explosions often take a spherical type shape unless there is some other outside influence taking place. When we take a look at explosions in space and galaxies and novas that are formed, a lot of times we will see them to be spherical in their shape. And the reason for that is the star that explodes, the object that is exploding, its center of mass is most likely wherever it is, and there are no external forces on this explosion that's important, and so, or noticeable, I should say, and so the center of mass of all the pieces of the explosion will still be where the object started. So unless there are odd pieces where there's a lot of where one piece has a lot of mass and another piece has a small amount of mass, they'll often take circular or spherical shapes because again, the center of mass would be right here in the middle, right here and right here actually. When looking at a car crash, everything that we just talked about with meeting up at the center of mass of the system does not apply. It doesn't matter how big one car is versus how big the other car is for the point of collision. What matters is how fast is each car going individually. And the major reason for this is the types of forces that are acting on the system. For the asteroids that collide, the only forces acting on the asteroids is the mutual force of gravity within the system. They are internal forces. So according to Newton's first law of motion, with no external forces, there will be no change in the system's motion, so they're going to meet at the center of mass. With the two cars driving down the road, we have external forces. There is a driving force of friction from the road acting on each car. Since this force is coming from the road and not between the two cars pulling on each other, they're they are not going to meet at their center of mass. So our big thing here when we look at when we try to use centers of mass is what kind of forces are acting on the objects in the system. If they're only internal forces, we can use centers of mass to find where an object is going to be or where they're going to meet up. But if we are dealing with external forces acting on the system, we can't use this at all. All right, so that's going to be a key thing on that. So it's kind of like, if you will, you're dealing with people in your family versus strangers. And let's say you have a good relationship with an older brother or sister, and you're, let's say, about 8 years old, and they say, hey, do you want to go to the mall? And you go, sure, and you go off to the mall. Mom sees you later on, goes, where were you? Oh, I was with my brother or sister. They took me to the mall. Oh, that's fine, okay. But some random stranger comes along and says, hey, do you want me to take you to the mall? The answer should be no. Now, what's the major difference here? The major difference is the type of relationship. When you're dealing with your family, it's internal forces. There's a very unique relationship there. If you're dealing with external people, external forces, that's a totally different behavior. And so we have the same thing here. So we are going to apply different rules to different situations just because how they're going to, just because how those forces are going to affect the objects and the system as a whole. Internal forces do not affect the system. Just like theoretically, the internal members of a family aren't going to try and hurt the family. External forces could try and hurt, could try and help. We don't really know how that's going to play out. With external forces of a system, they're actually going to cause some sort of change in the motion of the system. We just don't know if it's going to be beneficial enough for what we want. So here's a sample problem where we're going to just use centers of mass to find a meeting point. So I have two asteroids that their masses, the centers of masses are, of each one is 100,000 kilometers apart. Asteroid A has a mass of 600 kilograms and B has a mass of 1,400 kilograms. Due to their mutual gravitational pull between them, these two asteroids collide. How far does each one travel to reach the point of impact? And so first thing is, can I actually use centers of mass for this? And what we see here is we have the term due to their mutual gravitational pull between them. Okay, that makes this an internal force. It's between these two guys. It's mutual. I'm pulling on you. You're pulling on me. That is Newton's third law. And third law is always internal forces. So we have no other outside forces acting on this. So I'm going to just really try and use centers of mass. So the truth is, I'm being asked a totally different question than the one I'm seeing. Here I think I'm being asked for how far does each guy travel to reach the point of impact, but I'm really being asked how far away is each guy from the center of mass of the system. If I can figure out that, I now know how far each one has to travel. So I'm going to just simply set up a methodology to do this. So I'm going to need an origin. And so I'm going to pick a simple reference. And I'm picking point A. It could be object B. You could pick somewhere else. But I like one of the objects to be the reference. And I'm going to call that 0, 0. B being 100,000 meters away, I'm going to say is 100,000 kilometers, comma 0. I will now just simply find the centers of mass. The total mass of the system is 2,600 plus 1,400. The 600 times 0 is 0. The 1,400 times 100,000 is a very large number. When I divide that by 2,000, the total mass of the system, I come up with the center of mass being 70,000 kilometers away. So, oh, I should say away from point A. So the x position of the center of mass is 70,000 kilometers, comma 0. So now I just have to find how far away each object is. So 70,000 minus 0, A has to travel 70,000 kilometers. Object B is 100,000 kilometers away from A. But since the center of mass is 70,000 kilometers away, I just have to travel 30,000 kilometers for that guy. And so I just simply subtract out 70,000 from 100,000 and I'm done. Please notice B, the more massive asteroid, travels the least amount of distance. And that is because the center of mass of the system is always going to be close to the more massive guy. We could also think of this from a Newton's second law perspective if you wanted to, and third law. The mutual force of gravity, I don't know what it is, but I do know it's going to be equal on each guy, because whatever the force of gravity is on one, if it's an internal force, it's equal to the force of gravity of the other, just opposite in direction. So I'm going to have a negative sign here, and just because it's going negative. But if I'm just looking at quantities, I can ignore that negative sign. I can now turn around and say that this force of gravity, while internal for the system, is external for this asteroid. And the acceleration of the asteroid A would equal that force of gravity over 600. Mass, a force over mass. If I want to find the acceleration of B, well, the acceleration of B would be the force of gravity negative divided by 1,400 kilograms. Now, I don't know how big these accelerations are because I don't know the force of gravity, but I do know this. The acceleration of B will be smaller than A because there's more inertia, there's more mass. It's going to be hard to get this guy to move. And so it makes sense that B would travel the least amount of distance. Using centers of mass, I know exactly where they're going to collide, and I don't know the force. I don't know the accelerations. I don't know any of the speeds. But I know where they're going to collide. And so if that's what I'm looking for, I can solve this very easily without knowing a whole lot of information. So this is one of the key reasons why we want to use centers of mass when possible, because it gets us out of either doing a lot of work that we don't need to do, or it allows us to solve the problem we're missing that information that we really think we might need. Here we have an explosion. An explosion is just anytime two objects, or two or more objects, I should say, push apart very quickly. Here I have two lab carts. They are resting next to each other on a frictionless track. That means there's going to be no net external force. Now, if you're thinking there's going to be a force of gravity pulling down, you are totally correct. But there's also going to be a force of the table that's going to push up because the cars are not going to fall through the table. These two forces cancel out. That means I have no net force. And Newton's first law of motion, the law of inertia, does not say objects at rest stay at rest if there is unless there is an outside force. Newton's first law of motion, the law of inertia, says a system's motion does not change at all if there is, unless there is a net unbalanced external force. We do not have a net unbalanced external force. The forces all balance out to zero. So I can use centers of mass again. So um, in this case here, the cart A has a mass of 3 kilograms. B has a mass of 2 kilograms. There's a compressed spring that's between them, and they push apart. After 1.5 seconds, car A has traveled a distance of 30 centimeters. How far has B traveled in that time? I don't have to find speeds or accelerations. I just want to know the location of car B. So I can use centers of mass. Before, I didn't know where the center of mass of the system was. I had to find it. I had the location of the two objects. This problem here is the exact opposite. The center of mass of the system is right about over here. And since I have no net external force, that center of mass is not going to move. So I'm going to call the starting location where those two cars met as my reference. I'm going to call that 0, comma 0, the origin, and that's my centers of mass. I can now go ahead and, knowing the center of mass and the location of the 3 kilogram cart, find the location of the 2 kilogram cart. So I'm going to use my equation, and my total mass is 5 kilograms, 3 plus 2. That times my location on an xy axis of 0 is going to give me 0. My 3 kilogram cart is at a location of negative 30 centimeters. It's negative because it's to the left of my origin. If it was to the right, I would have made it positive. So 3 times negative 30 plus 2 times x. And I can now just simply solve for x. X comes out to be positive 45. It's positive because this object is going to be on the right. I'm not going to use the sign. I'm going to take the absolute value. So had these carts been reversed, had this been positive 30, this would come out to be a negative 45. And when I take the absolute value, I would still come up with 45. So when we are asked for distances, don't put a plus sign or a minus sign. Never worry about the sign at all. It is just for direction. If the question was, um, where has the object ended up? Oh, it ended up 45 centimeters to the right of where it started because it's plus. Where did the 3 kilogram cart end up? 30 centimeters to the left of where it started because it's minus. So we're going to use the plus minuses the same way you do in a math class for your XY coordinate system. For the very simple reason we're using an XY coordinate system to identify locations. All right, that's going to wrap up this video. It's nothing that's overly complicated. You're just solving centers of mass problems. It does take a little bit of practice, however. So I definitely want you guys to ask me questions about any of this. Remember, these videos are not going to replace me teaching. This is just to get you used to the concepts and introduced to it before we discuss and apply it in class.